Good morning and welcome to our first webinar in a series on how SMEs can save money by saving energy. This session will be on energy quality and power factor and how this applies to saving energy. This presentation will be performed by our partner Fuseco, the energy quality expert. Energy quality and power factors are a large part of saving energy. Poor energy quality and power factor make equipment use more energy and you get charged more for energy used. Next slide, please. The agenda for this webinar will be understanding energy efficiency and quality, harmonics and power factor considerations, and we'll be finishing up with a Q&A session. Drop questions in the comments and on LinkedIn, please. Next slide. Who are we? We are a dedicated team of professionals that offer easy, accessible energy efficiency audits. We do this so we can bring the energy savings of big businesses to SMEs. In short, we help you save money, energy, and the planet. Next slide, please. Energy efficiency and quality are a very important part of our mission to help you save energy and reduce your cost of operations. Next slide, please. I would now like to introduce Peter from Fuseco. Peter?
Thank you, Vincent. Next, yep. So thank you, everybody, for joining, and thank you for the opportunity to talk about these topics. They are two quite hefty topics, but we'll try to condense them into an understandable format, and particularly in relation to energy and energy costs. Next slide, please. A little bit about not so much also Fuseco, but also what we're looking at. On the left-hand side here, we're looking at industrial applications or commercial building applications that involve motors for HVAC systems, pumping, any kind of application. These days, they're often controlled by variable speed drives, which in itself does help create enormous energy efficiencies. However, there are several secondary effects, and we'll go through a couple of these. So we represent these brands that help consider these secondary effects and improve the power quality throughout the installation. Next slide. So traditionally, in the past, when I say traditionally, this is probably 50 plus years ago, we had resistive loads like hot plates and heaters, inductive loads like motors and so on. They have coils or chokes or reactors involved, and capacitive loads. So these are capacitor banks and so on in various applications. Next slide. Now we're going to go into a little bit more detail about these shortly, so I just wanted to briefly introduce these terms. Linear loads is what we see typically in industry today. These have zero harmonics, which is also something we're going to talk about, but can have poor power factor, which can lead to increased costs when we have to pay our distributor each quarter. We also have lots of non-linear loads, and it's actually increasing quite a lot. And this has been the case for particularly the last 20 to 30 years, just the increased use of variable speed drives and other rectifier-based systems that cause harmonics, but also poor true power factor, which we'll go into detail shortly about. Next slide. So what I'm going to do is combine maybe looking at the motor and variable speed drive. So if you can imagine on the right-hand side, we have the motor load in the application, so connected to a pump or fan and the likes. And then we have a motor controller called 6-pulse variable speed drive. So we're going to look at the secondary effects of the variable speed drive, but we're also going to talk about the motors themselves, which would be regarded then as a DOL application if it's directly connected online. Next slide. Okay, so I want to spend a little bit of time here. The first topic for today, power factor. There are actually different types of power factor. If we had a motor directly connected to the supply, then what we're talking about is the difference between the actual consumed power, represented here as P in the triangle over to the right, and S, the apparent power. So that triangle, if you just use old school maths, you'll see has a third side, Q. It's what's called reactive power. Reactive power, it is a hard one to sort of create an analogy for, but I often call it like a slinky effect, or you may see people trying to explain this as the froth on a glass of beer. So if you went to the bar, you get a beer poured for you. Depending on the beer, if it's a German beer in particular, you might get like 1/3 of a head. You're paying for that volume, and that's what's happening with displacement power factor. In most parts in Australia, you're actually paying for this Q proportion, but as a result of being billed in kVA hour, which is a part of the apparent power makeup. So apparent power is on your bill would be shown as kVA, or kVA hour, but it's a makeup of kVAR, so the reactive component, and kilowatt combined. So we're going to come back to that and maybe how to reduce this triangle down to the same length as P. And that's when you can save on the reactive power, save on your kVA hour costs. Now, if then look at the supply side of a variable speed drive, it does get quite a little bit complicated. The actual displacement power factor is reduced. So it is almost close to P, but this is to do with the internal components of that variable speed drive. However, the true power factor, which incorporates harmonic distortion, which we're going to talk about shortly, leads to the situation where we have a different value here. So your kVA total is also not ideal. The closer we get to 1, the better, the closer it is to resistive load. But you can see down the bottom here, 0.92. That's typical true power factor for a 6-pulse variable speed drive, the most common motor starter, motor controller in the industry today. Next slide. Now, if we look at the other topic, harmonics, so this proportion of true power factor that increases kVA, this whole topic is often referred to as a black art. It can be if you get into it long enough and detail enough, but the actual fundamentals are reasonably straightforward. If we look at the red signal here, it's not sinusoidal and it's not in line with the blue voltage signal. So basically we have a lumpy and bumpy current waveform, and very difficult to understand for those that do understand the maths behind sinusoids and so on. We can't just use root 2 and peak to calculate what's what. It's really difficult to understand what's going on here. So what we need to do is represent these lumps and bumps in some other way. So we use what's called a fast Fourier transform, or Fourier series, transform. And we then have magnitudes we can work with. So this one here, this red spike at F5, that represents a frequency that is 5 times more than the original fundamental. So the blue one would be 50 hertz. That first red spike, F5, could be 250 hertz. And if you overlap that onto the 50 hertz fundamental, then you'll see the camel hump waveform, and so on and so on. So harmonics is, I think it's important to understand, it's purely in electrical engineering for supply side analysis like this. It's purely a mathematical representation. And it's limited. According to ISC standards, Australian standards, we're looking at a restricted frequency range. We're not talking about high frequency EMC or RFI or other aspects of power quality that can also be analysed in a similar way. We're just talking about how to understand these lumps and bumps. So these lumps and bumps are impacting power quality, and as a result, kVA hour as well. Next slide, please. So power factor itself, we've determined, depends on the motor and the makeup of the motor, which is to do with how many poles there are in that motor, which is to do with how many inductors essentially inside the motor. The variable speed drive has internal components that can impact how much of a harmonic content you will have on the supply, or how bad the lumps and bumps or the camel humps are. So if we're talking about harmonic current distortion levels, then it depends on the makeup of that product, but also how easily it is to draw those peak currents from the supplier. So typical values are put into the manuals and so on for manufacturers, but it does also depend on the transformer and upstream fault currents and so on and so on. Voltage distortion is a direct result of the installation and the way the product is drawing current. So you can think of voltage distortion, you need to consider the relationship between impedance of the installation, cables, bus bars, upstream fault currents, the impedance of the transformer, and everything else. And if you can just maybe remember Ohm's law, in this case, V equals IR. In this case, we're talking about impedances, not resistances, but that relationship is definitely still valid here. It's just technically, mathematically, a little bit more complicated. So one last point, total harmonic voltage distortion and current distortion levels can be impacted by background distortion from other customers. They're also impacted by Dower loads and other resistive loads that can also increase the 50 hertz component and therefore the percentage of perceived distortion compared to a normal sinusoid. This is quite a hefty topic, so if you need more information on this, just contact Vincent and myself and we can furnish you with more documentation. I used to be a factory trainer for a couple of the global manufacturers, and this course went over 5 to 6 days, so it can get quite detailed, but the basics, hopefully you'll understand, are reasonably straightforward. Okay, next slide, please. There are lots of products out in the market that deal with power factor and harmonic solutions. We've got a number of here on the left-hand side, just basic chokes and reactors that we can use on the input, the variable speed drives, but also, as you see here, on the output as well. So we can clean up the input, make a horribly distorted current waveform into a much cleaner. It's still a little bit lumpy and bumpy, but far better. And on the output of variable speed drives, you can clean up this high frequency switching to a much cleaner sinusoid, or close to a sinusoid. This topic in itself is also a very detailed topic, the secondary effects on the output of variable speed drives. So it's more to do with disturbances to other equipment and so on, not so much to do with energy efficiencies. Next slide, please. If we look at power factor correction, I've got a case story I want to show you about power factor correction. So this could be for a whole building, a whole like an office block or a hotel or just a regular business. It's quite a common product to use when people are looking at improving efficiencies and saving costs, because as I mentioned before, the distributors and retailers, electricity retailers throughout most of Australia will charge per kVA hour. So we can just put one of these products in, engineer a solution to suit, have a target power factor, and then watch the savings as a result. So these cabinets here, we can have up to 900 kVAR in one unit. So there's a lot of expandability. We can have just from like 25 kVAR, 50 kVAR, 100 and above as modules, and quite easy to install. But I do want to get into the case story because we don't have a lot of time. So if you can go to the next slide, please. So I just wanted to show you a real world example. Now, if you want a copy of this, I'm more than happy to forward this to you, but you don't need to really see all of the final access data. But Hopefully you can see the colors. So on the left-hand side of this waveform, this shows the power consumption at a McDonald's in New South Wales. You'll see a little bit of red. That's kVA. So that's the one that you're getting charged for, kVA hour. The green is the actual consumed current. The blue is the kVAR component. So that's slinky effect or the froth on the beer. So we don't want that froth. We're paying for that froth. We just want to get rid of it. So you'll see this is an extended recording, and there's various processes that are changing over time per day. Once you get about 3/4 of the way over to the right-hand side, you'll see the blue go down almost to zero. So we've got a power factor correction cabinet installed now. It's listening and measuring, recording the current flow. It's trying to work out the displacement between the current and voltage, and then it's bringing back the current flow in line with the voltage. So you have no power factor. Well, very little power factor. That's the goal. So you see the remaining kilowatt consumption in green, but then you'll see the red disappear. The red is not actually disappearing at all. It's actually tucked in behind the green. So the arrows on that triangle that we saw before are the same in length. That's the only thing that's happened here. So the kVA is the same length as the kilowatt. You'll see a tiny bit of red here when the loads are very, very, very low. It's not a perfect system. So there's virtually no power, there's virtually no kVAR, and there's virtually no kVA, but it's not perfect and in really, really partial loadings, but it's pretty good. So we're going to zoom in on the next slide, please, Dan. So we just zoomed in on the right-hand side there, and you'll see kVAR, the blue, almost zero. The red is still there, but it's tucked in behind the green. So you're not paying for the froth anymore. You're paying just for the kilowatt hour. These cabinets, the power factor correction cabinets, obviously do have a capital cost. So we sort of work out, is it going to make sense for people to install these compared to their bills and what they're getting charged? So there is a bit of a tipping point there. And yeah, that's I guess where Vincent comes in and we'll try to help out in those scenarios. Next slide. So here we're looking at power factor itself. So power factor is a relationship between kilowatt and kVA. From the old maths, if you use the SOHCAHTOA on the triangle, the relationship between kilowatt and kVA, you'll end up with cos phi, adjacent over hypotenuse, kilowatt over kVA, cos phi, should be 1 if they're the same length. And once you start getting that angle, then you'll get a cos phi. Cos phi is power factor. So the power factor here, when you turn on the power factor correction unit, it goes from up and down, up and down, up and down to over on the right-hand side where it's close to 1. It's not perfectly 1. If you go to the next slide, please, Dan. And here we see the result. Now, it would be nice in this case to be able to see the numbers on the left, because we're talking about, for those that do have a big screen, we're talking about 0.998, 0.999, close to 1. So this is very, very close to a resistive load as seen by the supplier. These are the 3 phases. Now, we do also have functions on the power factor correction unit to help balance these phases as well. And I would have thought, I think Dave, my colleague, made a note here that load balancing wasn't included in this shot, but you can also balance the phases. And you can also reduce the need to go close to 1. So you don't need the power factor correction unit going flat out. You might have a target of 0.95, for example, and it'll save a little bit of the energy being used by the filter itself. to bring it to these high performance values. So I hope that helps. That's more or less an overview of how savings can be made. In Australia, it's a little bit complicated. Every state is not the same, or the retailers charge slightly differently. On the East Coast, pretty all of the bills for industry are kVA hour. There are also negotiated contracts with suppliers and retailers. In Western Australia, regular households are billed by kilowatt, but once you get to small businesses who are also charged per kilowatt hour, they have negotiated tariffs, network tariffs that include kVA. So we've actually done some research over here that you can also improve the costs, or basically reduce the costs spent on kVA hour by also reducing network tariffs as well. So particularly in the East Coast, though, we charge per kVA hour. There can be quite a lot of money saved by the introduction of a power factor correction unit where feasible. Okay, so Vincent, would you like to take the reins again?
Yeah, I think a really good analogy to some of your earlier slides on what the power actually looks like, and visualizing it. And I think where I visualize it is sort of as a very choppy sea with crossing waves. It's and in saying that, if you are to navigate that with a boat or a ship, it does take more energy to cross those sort of waves rather than a flat sea. And yes, some of these things that even in some analogies they ring true. So yeah,
it's a good analogy, and it's actually quite hard to come up with different analogies that make sense. So one I've often used in the past as well for power factor is, imagine that you have a box to carry and you need to carry it from one side of the street to the other. What's the most efficient way? Do you carry it yourself, or do you get a third party to deliver it across the road? So if you were to carry it across the road by yourself, that's where the analogies, they might fall apart. But if you had a third party involved, he's not very efficient. He's just sitting there scratching his head, but he's coming with the ride anyway. You still have to pay him. You still have to provide for his energy use, and it is a tricky one to provide good analogies for. But it's I think the most common one is the froth on the beer. Because it's quite easy to see, particularly those interested in beer, that you're paying for a volume that you're not using. In cases, it's a good engineering, I think, good engineering exercise to do for someone's plant to look at this. And it's not always about unit cost that we're trying to save, but also network tariffs as well. It's a little bit more complicated, but can also be done.
Peter, I think a really good example in this also is, I have a client that installed a couple of $1 million worth of laser cutting machines, and we asked them, well, besides your power usage, what's your power factor, and what's the harmonics coming off the machine? Because these laser cutting machines, they're very high tech, very sensitive type of equipment, and he didn't know, and in the procurement process, looking at those things was not something that they would look at either. So it's sort of one of those forgotten things that people don't think about until later, when they don't realize they've been wasting energy and money.
Yeah, that's right, and it can actually result in far more serious consequences as well. We got an inquiry the other day for active harmonic filter, because the retailer or distributor had written to say to one of their customers that have 3-4 large pumping applications, that the harmonic content on there that has been measured by them is too high. They need to rectify this within the next 12-month period, reduce the harmonic content down to the, in this case, Victorian Electrical Code of Practice regulations, or they'll be disconnected. So that's as simple as that. So it's quite an expensive afterthought. These are large applications, large pumping systems, large motor controllers that are 2 meters wide, almost 3/4 meter wide. So 2 meters high, 0.5 meters, 3/4 meter wide in little switch rooms out in a remote area. Now they've got to somehow cut that switch room in half, extend it to put on an extra harmonic filter. It's a very expensive afterthought. So engineering is definitely good to do before those types of installations as well. So not just improving power factor and improving or reducing costs for installations that already are running, or essentially what we're talking about is a brownfields upgrade.
Yeah.
But for new projects, it's definitely worth considering, because not only can you reduce costs in your long term, but you might be stung by having a poor power factor or poor harmonics into the future as well.
Yeah, and these things they can quite easily add up. A couple of cheap power supplies to your equipment, like a computer or other equipment. A couple of cheap LEDs installed, and before you know it, your air conditioning unit is working, is just ticking over and consuming a whole lot more energy than you had anticipated or had.
Yeah, that's right. It's
Poor.
As I mentioned earlier, this topic is quite hefty, and the more we get into it, the more detailed it become. And to the audience listening, you're more than welcome to get in touch if you want this type of information. One of the secondary effects by having poor harmonics in the installation is the impact that has on voltage. So if you, for example, have a commercial building with lots of HVAC applications, lots of variable speed drives, chillers on the roof, high power applications, and they're all driven by 6-pulse drives, if you don't get the harmonics right, the impact can be quite dramatic on voltage. Because if you can imagine the transformer supplying that infrastructure, it only has a certain capacity to deliver these peak currents. And if you go back to my notes before about Ohm's law, you've got to consider the dynamics with installation. So if the installation is straining and struggling to keep up, then it can impact voltage quite a lot, and you get what's called topping, which is taking the peaks off the voltage waveform. Yeah. And that, as a result, lowers your RMS voltage. So instead of 415 volt, it's lower and lower and lower now. If you're going to lower your voltage to an installation with all these different applications, the only way you can consume the same power as required is to increase current. So if you're going to increase current in your switchgear, your switchboards, your bus bars, the equipment that's installed, your efficiencies go down as well. So it has quite a few pretty ugly secondary effects. That's apart from resonances, nuisance tripping, transformers overheating and suffering from eddy currents, too much eddy currents and losses and so on. So yeah, there's quite a lot of secondary effects.
There are, and put on top what more and more businesses do these days is solar in inverters that have to transmit the energy based on certain parameters. If where voltage and power factor are changed depending on how much they are exporting and a lot. So all that creates it into a very, very interesting and complex sort of sea of information and data we have to contend with.
Kieran online has a good question, very good question. How could you determine if you're likely to produce poor harmonics ahead of an installation if you haven't used the equipment before? It's a good question. All of the manufacturers for variable speed drives have a reasonably basic, limited simulation tool where they can calculate the harmonic content for the variable speed drives that will be in use. It's often not quite enough, though, for the entire electrical installation. And that's where the consultants will come in with more advanced CAD tools and incorporate that data into a CAD simulation. So, like one of them could be PowerCAD or SCAD tools and high-wave modules and so on, where they basically collate all of the data. They do a simulation in the software, and it's surprisingly accurate. None of them take background distortion into consideration, so that's something to remember. But they do offer quite accurate simulation data to move forward and specify power factor correction or harmonic mitigation equipment. Hope that answers the question, Kieran.
And I think part of that question also is it's okay to pay a consultant a few hours and you select the right piece of equipment for your application rather than going with the cheapest quote from the electrician that you found after 5 minutes Googling.
Look, at Fuseco, we're very technically focused, and there's quite a lot of engineering focus. So most of the guys are very high level. Quite a few electrical engineers, so we help in that process as well. It's not straightforward, so we often will act as an intermediary between end users, contractors, and the like, and consultant firms, or as a group to try to understand what's required. We've got our own simulation tools for our own equipment as well, but we're often combining with a lot of the other tools to make sure that we're getting the right result. So it's not that straightforward, but there's definitely enough competence here to do that.
Well, on that, I might like to leave it there. Thank you very much for your time, Peter.
My pleasure.
And thank everyone else for your time. I hope it was informative. We will be following up by sending this presentation to everyone that logged in. And if you have any questions, please do reach out on the website or via LinkedIn. And thank you all for your time. Have a lovely day. Goodbye.
Okay then. Thanks, Vincent. Bye-bye.